So in last class, we were discussing about what happens when you have a closed system with pure liquid, water and vapor. So no presence of any additional gas inside the system. Then you will have the vapor pressure equals to the saturation pressure of this water at whatever temperature this entire system is at. So let this system temperature be some temperature T. So that would be the exerted vapor pressure. Now, in case you inject some non-condensable gas, let's say air, hydrogen, helium, anything, any gas which does not condense at this particular temperature, then you will have the pressure exerted by the gaseous phase will be equal to partial pressure of the water vapor plus the partial pressure of the gas which you are injecting. That would be equal to your total pressure. Okay, but at thermodynamic equilibrium, you will still have the partial pressure of water vapor equal to the saturation pressure for water at that particular temperature. So now you can understand that the composition of the non-condensable gas has absolutely no bearing on the partial pressure of water vapor, because this is still governed by the the properties of water. And when you have this condition where the partial pressure of water vapor is equal to the Psat at that particular temperature, then you will have rate of evaporation being balanced by the rate of condensation, and that would be the equilibrium condition. In case you reduce the partial pressure of water vapor, you will have evaporation occurring. In case you increase the partial pressure of water vapor now in this gas, you will have condensation which will happen. So you can consider this process of liquid to vapor and vapor to liquid. So at this condition, where the partial pressure is equal to Psat, you will have both evaporation and condensation being balanced out. If you reduce the partial pressure, your liquid will turn into vapor, so your forward reaction will be faster. And if you increase your partial pressure, you will have the backward reaction, which will be dominated. Okay, so the system will tend towards the equilibrium condition, that is Psat at this liquid temperature. Okay, and for thermodynamic equilibrium, this liquid temperature and vapor temperature was also assumed to be the same. If you have an equilibrium there also, then again we will have to reassess the entire thing. Now we discussed only the control mass scenario, where you will actually attain equilibrium, because after some time the entire vapor will have some amount of water vapor and of course whatever non-condensable gas you have injected, and the pressure will become Psat at that particular temperature. Now if I make this container like an open vessel, which is what we will see in most of our day-to-day processes, then what will happen is, if you imagine that there is a thin layer of air just above the liquid water, it will be saturated. So when I use the term saturated, it means that the partial pressure of water vapor is equal to Psat at that particular temperature. Now again, I am assuming that the liquid water temperature and the air temperature is same. Okay, so just above this liquid level, you will have a very thin layer of air which has water vapor corresponding to this Psat at that particular temperature T. But far away from this, it need not be saturated, which means that PV, that is the partial pressure of water vapor in air, is less than Psat. So it is unsaturated. Okay. So the first case is called saturated, where the partial pressure of water vapor is in the air is equal to the saturation pressure of water at that particular temperature. And this is the condition which we normally denote by RH equals to 100%. Whereas the far away, if I move away from this liquid column, the air could be unsaturated. That is, partial pressure of water vapor could be lower than the saturation pressure of water at that particular air temperature. So this is the condition where RH is less than 100%. So what is RH? RH is nothing but PV over Psat at that particular temperature. So there comes the definition of RH. So in last class, we were only discussing the saturated condition, and that saturated condition is very easy to attain in a control mass system. Everything is closed. So eventually you will attain the saturated condition. But when you have your top lid open, you are exposed to the ambient air. So the air just above this liquid column will be saturated. Further away, it is unsaturated. Now there is a concentration gradient of water vapor. So water vapor can now diffuse. So vapor molecules can now diffuse from this saturated layer to the unsaturated air. Okay. So then it will bring down the partial pressure of water vapor in this layer just above the liquid water. And that would be again replenished by some more water getting evaporated. Okay, and you can enhance this continuous evaporation process by blowing air. You put a fan, you blow air. So whatever water vapor molecule diffuse to this unsaturated air, you take it out and replenish this again with more unsaturated. That is what your fan will be doing. So if you have still air, again after some time you may see that the rate of evaporation will be less because this water vapor will move to the next layer and then the next layer, and it will try to saturate the air in the vicinity of this vessel. But if you put a fan, every time you will blow out this saturated air and bring in fresh unsaturated air. And eventually you will see that your liquid column continues to decrease. Okay, unlike the previous example which we were discussing, where the liquid column will not decrease once the volume inside that vessel was fully saturated with water vapor. Okay, so this is how you the drying of clothes happen, or if you just put a large container of water outside on a dry weather condition, you will see that the water uh, in the container continues to dry. Okay, you will be left off with nothing if you keep your container out for a long period of time. So ultimately, the evaporation process is uh, a combination of the phase change as well as mass transfer. So your evaporation will stop if you do not have this mass transfer. So your phase change process will stop because you will attain an equilibrium condition. So unless and until you have mass transport of this water vapor near your liquid column to far away from this, you will not be drawing in further uh, vapor from this container. So for the evaporation to continue, you require mass transport. Okay. And the potential for this mass transport is the concentration gradient of the water vapor in your air. Okay, again, air is just acting as a secondary medium. It can be any gas. Okay, if you take this container of water to Mars, even there also you will see the same phenomenon. Just because the atmospheric gases over there are different doesn't mean that you will not have evaporation there. Okay, the partial pressure of water vapor is completely dependent on the property of water. It has nothing to do with the property of air. Okay. Now you would have heard maybe in your school or maybe in some other forums or news that when you have RH equals to 100% or when it is very humid, you get rainfall or you have dew formation. So what happens is when you have air which is fully saturated, that is the PV over there is equal to the PSAT. Any further evaporation from any source, okay, just hypothetically assume that your RH goes to 105%. So what it means is now PV is greater than PSAT. So this additional 5% will actually condense into liquid. Okay, bringing back the air to 100%. Now this you can actually observe from your PV diagram or TH diagram or whatever for your pure fluid, pure water. This is your PV. Okay, let us first see what is the unsaturated condition, what is saturated condition, and what is this RH equals to 110%, what it signifies on the PV chart. Okay, this is liquid, liquid plus vapor, and vapor. So let's put some numbers. Let's say temperature is 30 degree. Correspondingly, the PSAT is around, I think 4 kPa or 3.5 kPa. Or let's assume 4 kPa. Okay. Now let's say the air has partial pressure of water vapor equals to 2 kPa, but the air temperature is 30 degree. So let's make it TB. Then it becomes much more easier to plot. So I can draw the isobars. So let's say this is the isobar for 2 kPa. And this is the isobar for 4 kPa. So this temperature will correspond to 30 degree because 4 kPa is the saturation pressure at 30 degree for water. Now, if your partial pressure of water vapor in air is 2 kPa at 30 degree, so if you extend this 30 degree line onto this 2 kPa, what state you get? You get superheated vapor. So it means that air has water vapor which corresponds to superheated condition. So definitely there cannot be any condensation. The limiting case will be when the partial pressure of water vapor is at 4 kPa. So then you reach this saturated vapor condition. Now let us assume you have 5 kPa pressure. Okay, let me draw the 5 kPa isobar. Now your 5 kPa is this. It will intersect the 30 degree line in the subcooled region. Which means that the state of water in air will be liquid. Now this is where the most fundamental assumption of psychrometry comes is air cannot hold liquid water. So by action of gravity, it will fall down. It will fall down as rain or dew or hailstorm or snow, whatever, it will fall down. Okay, but of course, you know from fluid mechanics, you can have drag forces on that liquid droplet. It can still hang in air. Okay, that is what you see. The foggy weather is basically liquid droplets hanging in air. But when we are making the psychrometry chart, discussing psychrometric processes, we will not discuss the misty or foggy situation. So you will always be limited to RH equals to 100%. RH equals to 110%, 120%, it means that you have liquid droplets hanging in air. Okay, so if you have this condition of 5 kPa, what will the actual process will be that your liquid droplets will fall down and the partial pressure of water vapor in the air will again go back to 4 kPa. So it will move from this to this. It will move from this 5 kPa line to 4 kPa. Okay. And whatever number of moles, so your initial number of moles will be P equals to whatever N initial RT by V. Let's say V is the control volume, the volume of the control volume we're looking. So this corresponds to 5 kPa. So you get the number of moles moles initially, and finally it is 4 kPa again, because RH equals to 100% is the maximum, is the condition at which your air can actually hold the water vapor. So again, you plug in 4 kPa here, you will get some other number here. So that difference in moles corresponding to 5 and 4 kPa is the amount of water which will fall in form of liquid droplets. From 5 kPa to 4 kPa, the difference in the number of moles, that difference is basically the amount of water which will be falling onto the ground, either in form of rain or dew, whatever. And now your air is again at RH equals to 100%, and this condition is back to your equilibrium condition. So if you have any degree of unsaturation in air, the air will tend to pick up moisture from any source available. If you have any degree of supersaturation in air, then air will drop down that additional moisture in form of rain or dew. Any doubts, any questions that come to your mind right now? So if you have superheated condition of water vapor in air, it is sustainable. If you have saturated vapor condition, that is also sustainable, but the subcooled liquid condition is not sustainable. Okay, so this is another assumption that we will make in all psychrometric processes. So that's why in your psychrometry chart, you will not see RH equals to 110% line. Okay, the maximum RH line will be 100%, that corresponds to saturation. So we have discussed all these things. Now, just one question before we look at all the definitions. Now, since we are treating moist air as two separate gases, one is dry air, which never condenses, and water vapor. So this is how we are going to treat moist air. Dry air plus water vapor. How many properties will be needed to fix the state point? Can anyone answer this? It's a mixture of binary gases. So dry air has all the other gases. You have nitrogen, oxygen, argon, CO2, and all other gases. So their composition is fixed. So we will treat it as one single gas, one single ideal gas. So that is one composition. The other gas is your water vapor, which we will treat it separately. So now if you have a mixture of two gases, how many properties are needed to fix the state point? So if I just give you pressure and temperature, will you be able to fix the state of this mixture? Yes. So you will also need an additional information on a mole fraction. Okay, what is the mole fraction of air or water vapor? So you can subtract 1 minus that mole fraction to get the other mole fraction. So you will also require the mole fraction or mass fraction. Okay, so not only pressure and temperature, but you will also require what is the content of dry air in your moisture or the content of water vapor in your moisture. So that information will also be required. So you'll always require three property information. But if you look at all the psychrometric processes, they will happen at atmospheric pressure. So what we eventually do is the psychrometric chart is drawn not in a uh, in a 3D manner. It is still drawn as a 2D sheet. Okay, so from this understanding, you require P, T, and mole fraction as three independent parameters to finally fix a state. But you will see that all the air conditioning processes or all the psychrometric processes that we will discuss for engineering applications, they will eventually happen at atmospheric pressure. So P is constant. So eventually, you just require two properties to fix the state point. So a corollary of this is, since we are fixing the P as 1 atmosphere or 1 bar, it depends on the charts. If you move to a place where the pressures are lower than that, let's say on top of Mount Everest, then your psychrometry charts will not give you the correct values. So you need to redraw the entire chart for that lower atmospheric pressure. So barring those special situations, we can still work with just two properties, assuming that the third property, that is the pressure, is constant. This barometric pressure is constant. So these are some of the important terminologies that you may come across in all the psychrometric processes. They are nothing new. So you will have mole fraction of dry air, mole fraction of water vapor. The partial pressure of dry air will be given by mole fraction of dry air times the total pressure. Okay, similarly, partial pressure of water vapor will be given by the mole fraction of water vapor times the total pressure. These are all things that you would have learned in your high school physics and chemistry classes. So this is an important terminology which is used and required frequently in all psychrometry processes, that is absolute humidity. It is also sometimes called as specific humidity or humidity ratio. They all mean the same thing. Different textbooks may have different nomenclature, but all these three terminologies mean the same thing. It is just the ratio of the amount of water vapor present in your air to the mass of dry air. Okay, the units will be either grams per kg or kg per kg. So grams of water vapor in kg of dry air. Okay, and then if you just do some simple manipulation in terms of the molar mass of water and molar mass of dry air, again molar mass of dry air is based on the composition of dry air. That is, in this most simplistic manner, if I assume it to be 78% nitrogen and 79% nitrogen and 21% oxygen, so then you need to determine what is the molar mass of air in terms of nitrogen's molar mass and oxygen's molar mass. Okay, so if you just do this simple manipulation, you will finally end up with this. So what this expression gives you is, you can know what is the absolute humidity if you know the partial pressure of water vapor in it. Because total pressure is fixed, so all it depends on is the partial pressure of water vapor. Rest is the ratio of molar mass of water divided by the molar mass of air. That is again a fixed quantity. So if you know the partial pressure of water vapor, you can fix omega, or if you know omega, you can fix the partial pressure of water vapor. Okay, and remember, as I told you, the potential for mass transport between your saturated layer just above your liquid column and the air which is far away from this container, that was, the potential was on the basis of omega. This omega gives you what is the amount of water vapor present in your dry air, or rather in your moist air, but it is on per basis, it is on the basis of per kg of dry air. Okay, so omega over here and omega far away is what drives the mass transport. If omega just above the liquid column is higher than the omega far away from the this vessel, then you will have water vapor transported from this to the air in this manner. If in case the reverse is true, the amount of water vapor present in your air is greater than the amount of water vapor next to your liquid column, then you will have water vapor transported from air to your liquid vessel, and eventually it will lead to condensation. Okay, so how it can happen? Let's say your air is at 40 degrees C and it is 100% saturated, 100% RH and 40 degrees C. So you will have your partial pressure corresponding to 40 degrees C. I think it is close to 8 or 9 kPa. Okay, and hence your omega will be corresponding to this 9 kPa. Okay, omega is dependent on partial pressure. Now assume you have a vessel which is at 20 degrees C. So the air just above this will be saturated at this temperature, 20 degrees C, just above the liquid column. So at 20 degrees C, the partial pressure is around 2 kPa. Okay, and hence the omega corresponding to this 2 kPa will be lower than the omega corresponding to 9 kPa. Now you have a potential of mass transport from the air to your layer just above the, from the bulk air to the layer just above the liquid column. So you will see that your container will become wet, so from outside and from also from the inside, and you will have condensation happening. Your liquid column will continue to rise. So everything can be understood on the basis of either partial pressure of water vapor or on the basis of absolute humidity, whichever suits you. But once we start discussing the psychrometry chart, you will see that dealing with omega is much more easier because that is one of the axes in the chart. And last terminology that we are going to frequently use is the relative humidity, which I have already explained. Okay, the definition is in terms of mole fraction. So actual mole fraction of water vapor in air divided by the mole fraction if the air is saturated at that particular temperature. So mole fraction is ultimately the ratio of pressures. Any doubts on this slide? It is better to clarify all the doubts right now, because once we move into the processes, then it will be very quick. So it's better to lay down the foundation as good as possible so that we can quickly go through all the psychrometric processes. These are some day-to-day devices that you would have seen, which uses all the psychrometric processes for their operation. Earthen pots, desert cooler. If you have gone by the Kolaghat power plant, if you go by train to Kolkata, you will see cooling towers installed next to the power plant, very close to the railway track. Okay, so they all use the various processes which happen uh, using the moist air. Okay, we have some very old cooling towers close to our main administrative building on the back side of that. We would have seen such old cooling towers made of wood. This is a very simple example. Estimate the maximum amount of water vapor that can be present in a room of internal volume 300 meter cube, a very big room. Barometric pressure is 101 kPa, temperature of the room is 30 degrees C and 25 degrees C. How will we go about solving this problem? We will assume ideal gas right now because nothing is given. So we'll assume ideal gas for air as well as water vapor. Okay, maybe I should have given that. Assume that water vapor is also ideal gas. If you make that assumption, can you estimate what is the amount of water vapor present in this room? So do you know what is the pressure? So you can apply PV equals to MRT, where R is the specific gas constant. What would be the pressure? Temperature is given 30 degree in one case, case P is 25 degrees. What would be the pressure?
Find the saturation.
Yes. So you just have to find the saturation pressure. That's it. At this temperature. So whatever mass you get, that is the mass of water vapor present in this huge room. So let's look at the other intensive properties like enthalpy, internal energy. So since we are dealing with mixture of two gases, that is dry air and water vapor, so the enthalpies will also be given by the summation of the two individual enthalpies. So mass of dry air into the specific enthalpy of dry air plus mass of water vapor into specific enthalpy of water vapor would be the total enthalpy of this mixture. Now I can divide this entire expression by the mass of dry air, and then finally what we end up is enthalpy of dry air plus omega times enthalpy of water vapor. Please remember, this is water vapor and not liquid water. Okay. So you see that the specific enthalpy of this mixture is defined again as per unit basis of dry air and not moist air. Okay, so mass that has been divided is not the total mass, that is Ma plus Mv, but it is just the dry air mass. Because we had defined omega also as mass of water vapor divided by the mass of dry air and not the total mass. And all the intensive properties in case of moist air is defined as per unit mass of dry air and not per unit mass of moist air. And the reason for this is all the cyclometric processes will involve change in mass of water vapor, but your dry air mass will remain constant. So let's say you have a shaft where you have cooling coil, air comes in, water vapor condenses on this cooling coil and air goes out. What remains constant at the inlet and exit is the mass of dry air. So if you had, let's say, 1 kg per second flow rate of dry air at the inlet, you will still have 1 kg per second of flow rate at the mass flow rate at the exit for the dry air. But if you had, let's say, 20 grams per second of moisture coming in at the inlet, you may have 10 grams per second of moisture going out. The rest, the remaining 10 grams condensing and falling onto this shaft as liquid water. So you see the total mass has now changed because your water vapor content can change between inlet to exit. But what remains constant is the dry air mass. So that's why it is just an engineering simplification that let's define all the properties on the basis of per unit mass of dry air. Okay, so now let's look at the cyclometry chart. So the cyclometric chart will have the pressure mentioned, what pressure has been used to make this chart. So on the x-axis, we have something called the dry bulb temperature, which is nothing but the temperature of the air. Okay. Now, again, there is a simplification that will assume that the dry air temperature, the moist air temperature, and the water vapor temperature in the air, everything is equal to dry bulb temperature. So there is no temperature in equilibrium between your dry air component and the water vapor component. So you have a thermal equilibrium between the components of the gases. It's not as if the nitrogen and oxygen is at some temperature and water vapor is at some other temperature. So as long as the mixture property is concerned, you have perfect equilibrium in terms of temperature across all the components of the air. So when I say dry bulb temperature of the air is 30 degree, it means the temperature of water vapor present in the air is also 30 degree. Okay. Now on the y-axis, what you have is omega. Okay, the units could be kg per kg of dry air, so kg of water vapor per kg of dry air, or it could be grams of water vapor per kg of dry air. I think here it is wrong. It should be grams because the numbers are 2, 4, 6 like this. It should be grams. Okay, very small amount of water vapor is present in air. So dry bulb temperature, absolute humidity. Then you have these curved lines. These curved lines are constant RH lines. RH equals to 10%, 20%, 30%, and the maximum is this saturated line, RH equals to 100%. Then you also have these slanted pink lines. So these are actually not very useful for the processes that we are going to discuss, but it is still drawn there. So these are constant specific volume lines, or you can also look at it as constant density lines. Now, what is more important are the slanted black lines. This denotes constant enthalpy. If you extend this, wherever it touches the scale, you can read the mixture enthalpy, again kilojoules per kg of dry air. So that is exactly what we defined as HA plus omega times HB. So this is that value. So all these black colored slanted lines are constant enthalpy lines. Okay, now you can also draw some additional lines which are not a part of this printed psychrometry chart. Is if you draw a horizontal line, it is constant absolute humidity. If you draw a horizontal line, it denotes a constant absolute humidity line. If you draw a vertical line, it denotes a constant dry bulb temperature line. So since we have maintained the total pressure constant, any two properties, if you know omega and dry bulb temperature, that is enough to fix the state of this mixture. Or if you know the omega and RH, okay, RH and omega, wherever they intersect, again that will fix the state of the mixture. Or if you know temperature and RH, that also fixes the state of this mixture. So you just need to have information of two thermodynamic properties. It could be any combination. Any doubts in the psychrometry chart? Anything you want me to repeat? Okay. So there is another line which is not visible probably at your end, is some dotted lines are drawn where this 25 wet bulb temperature is written. Okay, there are some other lines which are drawn parallel to this dotted line. It's not very visible. So they are constant wet bulb temperature lines, which we will see later. So whenever we are dealing with any psychrometry processes, there are two additional temperatures which will frequently again come across is dew point temperature and wet bulb temperature. Can anyone tell me what is dew point temperature? I think you would have studied this in your thermodynamics. Huh? What is dew point temperature? No one remembers. Okay. So let me help you with this. So let's take one step back. Let's look at the definition of relative humidity. It is the partial pressure of water vapor present in the air divided by the saturation pressure of water vapor at that particular T. So T denotes dry bulb temperature. Because we are assuming that water vapor, air, everything is at the same temperature, that is dry bulb temperature. Now, what are the ways by which you can attain RH equals to 100%? Let's say initially you have 50%, 0.5, 50% RH, and I want to make it to 100%. So there are two ways. Either you increase the numerator, that is you add some moles of water vapor in air, or you reduce the dry bulb temperature so that the denominator reduces. So that's the two way by which you can make this expression go to 100%. So the second way where you reduce the temperature of air and without changing the numerator. So that process is called the attainment of dew point temperature. So that process by which you can saturate the air without changing the partial pressure of water vapor. You simply cool the air. Just sensibly cool the air till you see the first droplet of water vapor condensing. That gives you a visual feedback of attainment of dew point temperature. Okay, again, if I go back to my previous example, let's say the temperature is 30 degree, corresponding to that, the saturation pressure is 4 kPa. Okay, let's say air actually has only 2 kPa water vapor. So I am over here. So unsaturated air, you will see invariably means the water vapor state is superheated. So this is your 2 kPa line and this is your 30-degree line. They intersect in the superheated region. Now I reduce the temperature of air without changing the partial pressure of water vapor. So without changing the partial pressure of water vapor means I will not change the amount of water vapor present in air. I will not touch that. I will just move along this constant PV line and till I reach this temperature. So now read this temperature. This will denote your dew point temperature. So this is drawn on a TV diagram of for water. I have not even looked at the psychrometry chart. So even without the psychrometry chart, you can find out what is the dew point temperature for the given condition of air. First, you plot the given condition of water vapor. You move along that same partial pressure line. Wherever it hits the saturated region, read that temperature. That is your dew point temperature. I don't need the psychrometry chart to get this value. But let's see how the process happens on a psychrometry chart. So if this is your initial condition, let's say this is 30 degree and this is your RH equals to 50% lag. What I am going to do is just sensibly cool the air without changing the partial pressure of water vapor. Remember, if you do not change the partial pressure of water vapor, omega will also not change. So there is no disturbance of amount of water vapor present in it. So it is going to be a horizontal line on your psychrometry chart towards the left because you are reducing the temperature. So wherever it hits the RH equals to 1 line, you read that temperature. This temperature and this temperature will be same. Okay. Any doubts in this? So this entire process is called the attainment of dew point. Okay, and this temperature at which you start seeing the first droplet of liquid water, that is called the dew point temperature. Now what happens if I reduce the temperature below the dew point? What happens when I reduce the temperature below the dew point? I started off here. This is where I start seeing the first liquid droplet, dew point temperature. What if I cool it further?
Condensation.
Condensation will happen. So what would be the process on this psychrometry chart is along this RH equals to 100%. Let's say I cool it further. Let's say this was 30 degree. 2 kPa means dew point temperature will be 20 degree. Let's say I cool it to 10 degree. So I will reach, theoretically I can reach this condition. So how much liquid water would have condensed? It is just the difference between the initial omega. This was the initial omega. This is the final omega. This difference will give me the amount of liquid which has condensed. Okay, at dew point, it is just the starting of condensation. It is the limiting case. If you reduce the temperature further, this is what will happen. Sensible cooling, and then you will have both sensible and latent cooling. Okay, instead of showing this entire process like this, what we do is again simplification of this process lines. We simply join the initial and final point like this. We'll show the entire process of cooling and dehumidification. So air becomes drier because we are capturing moisture and condensing it. This is the process which happens in your air conditioning. So your air conditioning systems have to operate at the evaporator coil has to operate at a temperature lower than the dew point temperature. If it operates at a temperature higher than the dew point temperature, you will not have any condensation. You will have some cooling, but that will just be sensible cooling. So in order to remove moisture, you have to condense. In order to condense, you have to go below dew point temperature. If you have any doubts, please stop. Please stop me at any given moment. This is just the graphical representation of what we have discussed. So this is your T2 is your dew point temperature. Now the next case is changing the numerator uh, where we add water vapor to the incoming air and saturate it. Okay, and the device that you would have seen which does exactly the same thing is your desert cooler. It draws in air. You see your desert cooler. It has a big fan. Okay, it draws in air from all the sides. It has a small pump inside. There will be liquid water inside this tank. There is a small pump and it sprinkles water on a porous material kept on the sides. It could be cellulose material, which we call as khaskhas, okay, or it could be some paper. Modern desert coolers have paper material arranged in a hexagonal shape or honeycomb structure. Various structures are available. So basically, you require a porous media, which allows air to pass through it, and it can also hold water. So you have air blowing over this wet material, and it picks up moisture. Again, over there also the potential to pick up moisture is based on the difference between the omega, so omega of the incoming air and omega of the air very close to that wet material. Okay, unless and until you have a large difference between these two omega, you will not have mass transfer happen. So if your incoming air is already saturated and the air which will be close to this porous material will also be saturated, you will see that the potential is negligible or zero. It can be zero. In places like Chennai, Mumbai, humid places. So there you cannot use the desert cooler. Whereas when it comes to Rajasthan, Delhi, there we have a very dry weather. So there you will have omega air much less than omega corresponding to this uh, temperature of this porous medium. Okay. So you will have omega saturation of this porous medium and omega air. So this has to be as low as possible. So it picks up moisture. As it picks up moisture, it becomes saturated. So it will not be exactly saturated, it will be close to saturation. So what you get over here from this fan is almost saturated air. So it could be RH equals to 80 to 90%. But as it picks up moisture, what happens? What happens? So we are saturating air. That is quite easy to understand by means of evaporation. But how do we get that thermal comfort? So as air picks up moisture, there is evaporation happening. And now evaporation is associated with some enthalpy change, isn't it? So liquid water, which is being sprinkled onto this porous media, is getting converted into water vapor. So there is HFG. Phase change, associated with that phase change, you will have huge amount of enthalpy change. So who is supplying this enthalpy? The air itself. The incoming air itself is supplying the enthalpy. So water picks up the enthalpy required for it to change its phase from liquid to water vapor. Okay, so then the incoming air cools down. The same process happens in your earthen pot. The enthalpy required to change the phase of liquid water present in your pot to water vapor is taken up by the water present in the pot itself. So pot as well as the water which is present there. Okay. So same phenomena happens over here also. The enthalpy is supplied by the air itself. And hence the air cools down sensibly, but it also becomes saturated or close to saturated. Okay. So this is the process which happens in your desert cooler. And the theoretical limit to which you can go by this process is called the wet bulb temperature. So you cannot cool down your air to uh, any arbitrary value. So there is a thermodynamic limit, and that limit is the wet bulb temperature. You cannot cool down the air below this temperature. So how the wet bulb temperature is attained? Let's say again you have air entering an insulated shaft. You have that wicking material. Okay, it's again a porous material which draws liquid water from this vessel. Okay, and as evaporation happens, the liquid height will go down, so we have to supply some makeup water. This is what you do also in a desert cooler, but you do not do it continuously, you do it in a batch mode. So before operating, you fill up your tank up to a certain level, and again, after operation, you have to refill the tank. So that makeup water is supplied over here. Okay, this entire box has to be insulated. Through this wick. Whatever temperature of air you get at the exit, that temperature is wet bulb temperature. Okay, in a desert cooler, you may not have complete saturation. Because just like heat transfer, mass transfer also requires lot of area. In order to have perfect mass transfer so that you saturate the incoming air, you will require infinite area between the incoming air and the liquid droplets. So you cannot provide infinite area. So the entire mass transport process can be seen as analogous to heat transfer process. In heat transfer process, the driving potential is temperature difference. Here it is the difference in omega. Omega incoming and omega of air just close to this wicking material. Okay, so this is the driving potential, but you also have area, which is an important factor. So if you have 1 liter of water and you spread it in, let's say, in a vessel which has 2-inch diameter, and you spread the same amount of water in a vessel which is 10-inch in diameter, you will have evaporation which is faster in that larger diameter vessel by virtue of larger area being exposed to the air. Very similar to your heat transfer process also. So in your desert cooler, even though you want it to be saturated completely, but you will not be eventually be able to get that. So there is again effectiveness of the mass transport process, which will limit you. So in case you were able to completely saturate the air, then whatever temperature you get at the exit, that is the wet bulb temperature. Okay. So if I write the first law, assuming that the fan work is negligible here. So let me draw the control volume in this manner. So this is the incoming enthalpy. This is the outgoing enthalpy of air. So Ma dot, again, dry air mass flow rate times the specific enthalpy. This is the outgoing Ma dot into H2. Plus you have some enthalpy of this makeup water. Now, how much makeup water has to be supplied? It is nothing but Ma dot into omega 2 minus omega 1. So whatever the incoming omega is, whatever the exiting omega 2 is, this difference is what you have to supply as makeup water, because that much amount of water will vaporize and it will be drawn by the air. So Ma dot times omega 2 minus omega 1 is the supply water into the liquid enthalpy. This is also into this control volume. So this is your entire first law expression. Now you see in this expression, you know H1, the incoming condition will be given. You do not know the temperature at the exit because that is what is WBT unknown. Okay, so hence you do not know W2 also or omega 2 also. If you started off from here, you are moving somewhat like this. Okay, all you know is at the exit RH equals to 100%. You do not know this temperature if you look at this expression. But this expression is just a function of temperature only, because if you know the temperature, you know RH at the exit is 100%. You can then get to know W2 and you will also get to know H2. It is an expression in temperature, but it is not an explicit equation. So you can make a guess and try to find out what is the how much you are off from zero. So you can do a hit and trial, or to make our life easier, these dotted lines are given. So if you follow from any state point, so if your initial condition is this, incoming condition is this, if you follow along this dotted line, wherever you hit this RH equals to 100%, that is your WBT. If you are in between these two dotted lines, if you are here, you draw a line parallel to this dotted line, and wherever you hit the RH equals to 100%, that will give you the WBT for that incoming condition. For solving this will require some hit and trial. You assume some T2, get the H2 value, get the omega 2 value, check if this leads to a summation of 0, then you're fine. Otherwise, you have to make another guess and you have to continue this process. So in order to make our life easier, this line is graphically represented, or this expression is graphically represented by this line. Okay, so wherever you reach this, that temperature you read, that is your wet bulb temperature. And you will see invariably your dew point temperature is always lower than the wet bulb temperature. This is your dew point temperature. This is your wet bulb temperature. Any doubts or any queries? So please stop me anytime if you feel that something is not clear. So now we can see that any process on the psychrometry chart will be accompanied by two changes. One is change in omega and the other is change in temperature. So if you have just change in temperature, then that process we call as sensible heat transfer or sensible cooling or heating process. Okay, so it is a sensible process. If you have only change in omega without any change in temperature, then that process is called the latent process. Okay, but you will see all the processes will be accompanied by both of these phenomena. Both there will be change in omega as well as change in temperature. So in order to determine the process, if I have to draw the process line on the psychrometry chart, I need to know if I know the initial state point and final state point, then straight away I know the process. But suppose I know the initial state point and only the net change in enthalpy between the initial and the final condition. I repeat, suppose I know only the initial state point and I do not know the final state point, but I know the final enthalpy. That is, I know H1 minus H2. Then if I plot the H2 line, this is the entire isenthalpic line. The process could be this, the process could be this. So all these processes will denote the same enthalpy difference. So I cannot fix the process line if I just know the initial state point and the change in enthalpy. Okay. So Q total, which is equals to MA dot into H2 minus H1. That is, let's say you know that. Okay. So from here, and you also know the initial state point. But if you go and check on the psychrometry chart, you will see this is the H2 line. Now, where exactly on this H2 line I lie, I don't know. I cannot fix it. So what we introduce is another parameter which needs to be fixed in order to fix the process, and that is that is called the sensible heat factor. What is the sensible heat factor? Is fixing the slope of this line. As I told you, once you know H2, you can draw multiple lines starting from your initial state point. So what fixes this slope is the amount of total heat transfer is this. What fraction of it is latent or what fraction of it is sensible, that one of them needs to be known along with the total heat transfer. So let's say I say that the total heat transfer is 20 kilojoules per kg of dry air. So this difference is fixed. And I say out of the 20 kilojoules, 5 kilojoules is latent heat transfer, which means that this minus this is the latent process. This is equal to 5. So this part is also fixed. So 20 is fixed, 5 is also fixed now. Now I can finish this triangle. So I go to a point below this where the difference is 5. And I already know that this is, let's give some number, 100. This is 80 kilojoules. And let's say this is 95 kilo. So once you have all this data, then you can fix the process line, because now you have 1, 2, 3, 3, 2, 2, and you can finish off this entire triangle. Okay, so just knowing the total enthalpy change across the process will not be enough for you to fix the process line. If you know the outlet state, that is good. If you know the in state and the exit state, that is very good. That fixes the process line. Many a times you will see that you just know the enthalpy difference. So then you also need to know additional parameter to fix the process line. That parameter is the sensible heat factor. So it is indirectly fixing the slope of this line. So sensible heat factor is defined as what fraction of your total heat transfer is sensible. Or you can also call another factor as latent heat factor as 1 minus sensible heat factor. Okay, so either you should know what is the latent heat factor or you should know what is the sensible heat factor. Okay. Now from the chart, it is straight away easy to read the enthalpies. Okay. So if you know 5 kilojoules is the 20 kilojoules is the total enthalpy change and 5 kilojoules is the latent one, then you can read everything from the chart. If you don't want to use the chart, there is another way. Another way of doing the same thing is the latent heat transfer will be given by Ma dot H3 minus H1. Okay, H3 minus H1. And that will only be equal to omega 2 minus omega 1 times HFG. Why? Because there is no sensible heat transfer. Along this line, there is no temperature change. So all the change in enthalpy is happening because there is a change in moisture content. So amount of water vapor at this state and at this state is different. So that difference in moisture content times the latent heat of vaporization will give you the enthalpy. So that will be equal to this. Whereas if you look at the sensible part, that is 322 process, that is again Ma dot times H2 minus H3 will be equals to Ma dot Cp of moist air, Cp of moist air times T2 minus T3. So here it is just Cp delta T. There is no contribution of omega because omega is constant on this horizontal line. Okay, so in your EES, if you use, so EES has already all this information fed in. So if you just give the values of omega 1 and omega 2, it will quickly tell you what is the latent component. But anyway, since we have to now use the charts, so in the charts, you will have to draw these lines which are parallel to those black dashed lines and read the enthalpy from here. Any doubts or anything that needs any re-explanation or repetition over here? Okay, so let's see what are the various types of processes which we can identify on the psychrometry chart. So if your starting point is this, if you move towards left along the horizontal line, then that process is sensible cooling. And this will happen if you have air incoming and there's a cooling coil. The cooling coil temperature, let's say incoming air is again at 30 and dew point is, let's say, 20. So if your cooling coil temperature is 20 degrees C, you will have this horizontal process. If your cooling coil is at 21 degrees C also, you will still have this sensible cooling. But if your cooling coil is at 19 degrees C, then you will have cooling as well as dehumidification, because now your temperature, coil temperature is lower than the dew point temperature, which is 20. So I'm still using the same example, 30 degree and 50% RH. Okay, so you will have sensible cooling as long as the incoming air strikes a coil whose temperature is equal to dew point temperature or higher than dew point temperature. But if your coil temperature is lower than the dew point temperature, then you will have cooling as well as dehumidification, because you will have this and then this. First process is just sensible cooling. The next analogous process in the heating side would be sensible heating. So instead of having a cooling coil, you place a heater. So you will have the sensible heating process. This process is called the cooling plus humidification process. This is exactly the process which we discussed in your desert cooler or the wet bulb temperature attainment. Okay, you are cooling the air, but you are also humidifying the air. So cooling plus humidification. So how to identify humidification or dehumidification is check the initial state point, check the final state point moisture content. If the final moisture content is higher than the initial, it is humidification. If the final moisture content in air is lower than initial, it is dehumidification. So all the processes will have cooling or heating that corresponds to the temperature change, as well as humidification or dehumidification, or you can also have processes where there is no change in humidity ratios. Okay. Cooling plus dehumidification. This will happen if you have a cooling coil temperature lower than the dew point temperature, like this. And as I told you, we will just denote the entire process by joining the initial and final point. So this is your cooling plus dehumidification process. The analogous opposite process would be heating plus humidification. So let's say in your incoming air, you supply steam. You supply steam at 100 degrees C. To incoming air, which is again at 30 degree and 50% RH. So because of the steam, it will pick up moisture, as well as the steam being at 100 degrees C will also heat the incoming air. So you will have heating plus humidification. Next is heating plus dehumidification. This happens when you pass the incoming air over material like silica gel, zeolite, which has affinity to water vapor. So as air passes over those material, it gets dehumidified, but it also gets heated up. Okay, because when water vapor goes into the pores of silica gel, it releases heat. So just like we had the horizontal process lines, you can also have the vertical process lines, like only humidification or only dehumidification. Okay, but attaining only humidification without any temperature change, or attaining only dehumidification without any temperature change by a single process is very, very difficult. You will always have some accompanying temperature changes also. It is very easy to sensibly cool the air or sensibly heat the air, but it is very difficult to have just humidification without any change in temperature, or just dehumidification without change in temperature in one single go. You can follow other process lines. You can follow this and then heat. You cool and dehumidify and then heat. Finally end up over here, so that the final process is effectively same temperature line, but only dehumidification. That is possible. But in single go, going from here to here, it's next to impossible. So we do not have any physical process examples where we can just go vertically up or vertically down.
Sir,
Yeah,
so in the previous, so in the psychrometric chart, means the previous page.
previous page.
Yes, sir, the cooling plus humidification is a constant enthalpy process, right?
Cooling plus humidification is not necessarily a constant enthalpy process. Because if you look at the wet bulb temperature attainment, that was also not constant enthalpy, because you had the enthalpy of the incoming liquid. Can you appreciate this?
Yes,
So you have, yeah, tell me.
but sir, the wet bulb, the lines, the dotted lines, they are parallel to the constant enthalpy.
They look parallel, because the omega 2 minus omega 1 times H liquid, this number comes out to be very small, and it looks as if the process line is H1 equals to H2, because this product is very small, because omega 2 minus omega 1 is of the order of few grams, and even if you multiply with the liquid enthalpy, it comes out to be very small compared to H1 and H2. It looks parallel, but it is not.
Okay.
But we need not always follow the wet bulb temperature line also. So it is just that as long as you follow this slope, this is also cooling plus humidification. This is also cooling plus humidification. This is also cooling plus humidification. So that wet bulb line is one of the cooling plus humidification process line.
Okay.
See, in the wet bulb temperature attainment, there was one very important criteria, that is this shaft has to be insulated. Your desert coolers are again not insulated. So you have some sensible heat transfer from the ambient. Okay, so you do not actually follow the wet bulb temperature line in your desert cooler. You may have some gain in enthalpy because of heat leak from outside to inside. So your desert cooler, the box inside is cooler, outside air is warmer. So you can also have some conduction through the box walls. So you will never be able to attain the WBT in your desert cooler. Okay, so instead of following the WBT line, you will end up following this flow. There will be some increase in enthalpy because of conduction from the ambient. This is just some general process lines which I had drawn. Okay. Need not be exactly on the WBT line. It looks, yeah. I'll change this. Maybe it is creating that confusion. It can be this line also. Any other question? Or any follow-up question?
No, sir.
So in the next few slides, we will just quickly go through some example problems on each of the process lines which we have seen. Sensible cooling, sensible heating, cooling plus dehumidification, heating plus humidification, heating plus dehumidification. Okay, so all those 6 processes, and the 2 processes which I told you are not possible physically in one go, that those I will not be discussing. So that is only humidification and only dehumidification. Because for them, we require two processes at least to accomplish that single vertical line. So this is the case of sensible cooling, where your cooling coil temperature has to be greater than or equal to dew point temperature, but of course less than your dry bulb temperature. So air comes in, passes through the cooling coil, gets cooler, comes out. No change in omega. That is the most important thing. Omega 1 equals to omega 2. And now you can apply your first law equation, taking this as your control volume. Ma dot H1 is inlet enthalpy minus Ma dot H2 is the exit enthalpy, plus Q dot being the heat transfer from the cooling coil. Okay, and then omega 1 equals to omega 2. So these two, if you simultaneously solve, you will be able to obtain the condition at the exit. So how this can be achieved in the practical scenario is you have your refrigeration system. Your evaporator coil has refrigerant coming in after your throttling device in liquid plus vapor state and exiting the cooling coil at least saturated vapor. It could be superheated region also. And incoming air strikes this coil. Your cooling coil temperature has to satisfy that condition, where it has to be greater than or equal to your dew point temperature, but less than the incoming dry bulb temperature of air. Then you will have only sensible cooling. So this is an example problem. You have a cooling coil, air at this rate. So if nothing is mentioned, you assume this as the mass flow rate of dry air, 2.4 kg per second of dry air. So this is the mass flow rate of dry air, which is incoming into your cooling coil at 30 degrees C and 50% RH, and it is sensibly cooled to 20 degrees C using chilled water, which enters the heat exchanging coil at 12 degrees C. So this is not a refrigerant cooling coil. This is a water-based cooling coil. So you have this cooling coil. Water comes in at 12 degrees C and leaves at 18 degrees C. And air comes in at 30 degrees C and 50% RH. And it sensibly cools to 20 degrees C. Okay. So what is asked is what is the required chilled water flow rate. So what should be the flow rate of water through this cooling coil so that you can achieve this process? So it's again quite simple. You obtain what is the net heat transfer from the air side. Air side, you can look into the psychrometry chart. This is your, let's say 30 degree, 50% RH. It sensibly cools to 20 degrees C. You read the enthalpy at these states. This is the omega 1 equals to omega 2 line. So if you use your psychrometry chart, you will see a lot of calculations are not even required. You just have to plot the process on the chart and you straight away get the data from the chart. Okay, read these two enthalpy lines. Whatever is the difference multiplied by 2.4 kg per second will give you the net heat transfer on the air side. That has to be balanced by the cooling coil. I know the temperature difference on the cooling coil side. I just require the MW. MW into Cp of water times delta T will give me the required mass flow rate. That will be equated to Ma into H1 minus H2. What is the cooling capacity? So you would have already determined in order to solve the first part. What is the cooling capacity? In tons it is asked, so you just have to divide it by 3.516 kilowatt. And what is the wet bulb temperature and relative humidity of air at the exit of the cooling coil? So it is asked at the exit. So this is your initial state. Let's say this is your final state. If you have to find out what is the wet bulb temperature, you have to follow that dotted line. Wherever it hits the RH equals to 100%, that is your wet bulb temperature. And relative humidity, you can straight away read. Okay, in case it lies between two relative humidity line, you approximately interpolate between the two RH lines. I think the RH lines are typically drawn at an interval of 10%. So if it lies in between, you can approximate that value. So if you have to work out a problem on sensible heating, it is very similar to the previous case only. I have not given any example. So if you see such devices placed in your air ducts, normally such devices are placed in central ACs. So they look like again tube fin arrangement, but you have the electrical heating coil inside this tube. Okay, and air hits this and gets heated and comes out. Okay, as I told you that in case you want only this process to happen, that is purely dehumidification without change in temperature. So what we normally do is we pass it through a cooling coil which has a temperature lower than the dew point temperature. So what you do is you cool and dehumidify, and then you raise the temperature back to its initial so that you obtain your desired condition. So many central ACs you will see after it comes from the refrigeration system where it is cooled and dehumidified, air is cooled and dehumidified. It then passes through a heater to bring the temperature back to the desired temperature. Okay, so now you should understand the fallacy of the dry mode which is present in your AC remotes. Okay, that does not just it dehumidifies the air, it dehumidifies and cools the air. For it to be just a dehumidifier and no change in temperature, you need an electrical heater again. Okay, so when you go to the dry mode, what it does is instead of following, let's say from here, if it was following this process line, it will cool further. Okay, it will cool further so that you dehumidify further. That's all it does. Okay, in fact, you will feel very cold if you use that dry mode in your AC because it only has a cooling coil. So all it can do is cool and dehumidify. It cannot attain only dehumidification. Okay, so the next process is what I was just now discussing, cooling and dehumidification process. Again, you require just a cooling coil, but now the condition is it has to have a temperature lower than the dew point temperature. Okay, now over here also, you will see this is the first law. Over here, you will again have some liquid water which comes out of your control volume. This also happens in your AC. You will see if you have a window AC, water continuously drips from the backside of your window AC, or if you have a split AC, there is a small rubber pipe which goes out through the wall, and that continuously drops all the liquid water out in the outdoor. But the amount of water that comes out into the liquid enthalpy, you will see again it is very, very small amount. But to be accurate, we have to account for all the enthalpies. So this is the enthalpy coming in. Enthalpy going out will be Ma dot into H2 minus the enthalpy of the liquid which collects in this and it is taken out, plus of course the Q coil, that is the cooling coil heat transfer. Okay, and the amount of liquid which is condensing is nothing but ma dot into omega 1 minus omega 2. So the apparatus that we use is same. Again, we have the refrigerant coil. You have refrigerant entering in liquid plus vapor, coming out as saturated vapor or superheated vapor. But only thing is now you're maintaining the coil temperature below the incoming dew point temperature. So incoming air's dew point temperature. And this is your process. Okay. Now, I think in last class, someone asked me that if I have to dehumidify in your air conditioner, why do we say that the load on the system is higher? Okay, so let's say this is your incoming air temperature. In one case, you are going through this process. Let me steeper. Let's say this is your incoming air, and in one case you are going through this process. This is your constant enthalpy lines, H1, H2. In another case, you are going through this process line. In one case, you are going through this. The other case, you are going through this process line. Now, there is a drastic difference in the coil temperature for process 1 and process 2. Even though the difference in the inlet and the exit enthalpies are same. Okay, so for process 1 also you have H1 minus H2. This is the difference. So process 2 also, this is the difference. But the slopes are different for process 1 and process 2. In process 1, you are only dehumidifying corresponding to this level. Whereas in the process 2, you are dehumidifying much more and your sensible change is less. So what is the difference in these two processes? So that would be given by something called as the apparatus dew point. So we already know that in order to have cooling plus dehumidification, we have to maintain a coil temperature lower than the dew point. So if I draw a horizontal line here, this is my dew point temperature. My coil temperature has to be lower than this for cooling and dehumidification to happen. Now, what should be that value? How much should I maintain? That is determined by the apparatus dew point. Okay. So eventually what is happening inside or on the outer surface of the coil is both heat and mass transfer is happening. Okay, simultaneously both of them is happening. And you eventually move along this path. Now, if you extend this process line and intersect at your RH equals to 100% line, whatever temperature you get over here is the apparatus temperature that needs to be maintained for you to follow this process. I'll repeat. Let's say your final state point is state 2. If you extend that and wherever it intersects your RH equals to 100% line, you check what that temperature is. That is your apparatus dew point temperature, or in simple word, it is your coil temperature that you need to maintain so that the incoming air follows this process line. Okay, there is a lengthy derivation for proving this. I will not go into that. But what you need to understand is this slope has to be matched by your coil temperature. This is your incoming temperature. If your coil temperature is this, you will move along this slope. If your coil temperature is this, you will move along this slope. That is the psychrometry process that your air will undergo based on your coil temperature. Okay, instead of using the coil temperature, a technical word is used called as the apparatus dew point. So what is meant by apparatus dew point is if you had 100% effectiveness in your heat and mass transfer process, then if you reach your apparatus or coil temperature, you will have saturated air exiting your coil at your coil temperature. If you have 100% effective heat and mass transfer in your cooling coil, then your exiting air will be at your cooling coil temperature and it will be saturated. Okay, but due to the ineffectiveness in the heat and mass transfer process, we will never attain this point. Your exiting air will be somewhere in between 1 and your apparatus dew point condition. It could be here, it could be here, it could be here, based on the area available for your heat and mass transfer process. This is like effectiveness of a heat exchanger. So if you have a cooling coil and let's say cooling coil is at 10 degrees C, incoming air is at 30 degrees C, air can reach 10 degrees C, that is the theoretical limit, but it will not reach 10 degrees C. It will be anywhere between 30 and 10, the exiting air. Because in order to attain 10 degrees C, we will have to provide infinite surface area. Something same is true in case of mass transfer also. So both are happening simultaneously here. So now you can realize that if you have to follow a steeper slope, okay, so if you have to follow this slope or if you have to follow this slope, both lead to similar enthalpy difference. But here you have to maintain a higher apparatus dew point. In this steeper slope, you have to maintain a lower apparatus dew point. So lower apparatus dew point means lower coil temperature, which means lower evaporator temperature. Okay, so here if your coil temperature is 12, here you may have to maintain 8 degrees or 10 degrees. So if your latent load on your cooling coil increases, even if your total load is same as the previous case, if the latent load fraction of the load increases, you have to maintain lower and lower coil temperatures. Which means that your compressor will have to now work across a higher pressure ratio. Hence, people say that if you have to dehumidify a lot in your AC, the load on the system is high. The load on the system, what they actually mean is the pressure ratio across which the compressor has to work is high because your evaporator temperatures will now have to be maintained lower. And that is exactly what the manufacturer does when you press your dry mode. When you press your dry mode, it lowers down the evaporator temperature so that you dehumidify more. There is no smart control over there. You are the control. If you feel that it is now too cold or too dry, you will automatically increase the temperature or move to the comfortable mode. We will change the mode. Questions, doubts? No questions? I hope everything is clear then. Okay. So if you know your apparatus dew point temperature, that is your coil temperature, and if you know what is the effectiveness of your heat exchanger, Okay, because this is eventually a heat exchanger. Then you can actually find out what would be the exit temperature from my coil. If I say that my heat exchanger is 80% effective, let's say incoming air is at 30 degrees C, coil temperature is, let's say, 12 degrees C. So 30 minus 12 is 18. 18 degrees C difference I should get theoretically, but I will only get 80% of this 18 degrees C. Okay. So how much it is? So 14.4 degrees C difference I will get. So I will have eventually the exiting temperature as 15.6 degrees C, somewhere here. And you join this line, 15.6 degrees C you mark, whatever omega you get, that is the amount of dehumidification you will get. So join this 12 degree and 30 degree C line. You know the effectiveness. Let's say if it is given 80% effective, 70% effective. Okay, then you know this intermediate temperature. And from here you read the omega also. So this difference is your amount of dehumidification. Okay. Now the air conditioning industry, instead of using the effectiveness as the parameter, they use something called as the bypass factor, which is nothing but 1 minus effectiveness. Okay, they will say instead of saying 80% effective, they will say that 20% is the bypass factor. Okay, they mean one and the same thing. So I think one of the question in your lab, I think the third experiment on air conditioning, one of the question was what is the bypass factor of the coil or something of that. What is the ADP bypass factor of the coil? So now you should be able to calculate that. So once you draw the process line, you extend it wherever it hits. That is your RH equals to 100% line. That is your ADP. And based on this temperature, air inlet temperature and the air exit temperature, you should be able to find out what is the effectiveness of the heat exchanger or bypass factor. So these are two complementary terms. Okay, and if I ask you what is the sensible heat factor, so since it is for the coil, so the coil term is added. So what is the sensible heat factor? It is nothing but if you draw these enthalpy lines, you complete this triangle. This is your 1 dash. So this is your total enthalpy change. This is your sensible enthalpy. This is your latent enthalpy change. If I ask you what is the sensible heat factor, this divided by the total heat transfer. I think these things are asked in one of the experiments at the end. Based on the data you get from the experiments, you can find out all these parameters uh, for the cooling coil used in the experiment. So what does the effectiveness or bypass factor of the heat exchanger depends on? It is basically the area. That is the most important thing. So if you increase the number of rows of the evaporator coil, okay, that will decrease the bypass factor, or in other words, it will increase the effectiveness. Or if you increase the number of fins, so you increase the area. Or if you increase the heat transfer coefficient, that will also improve your effectiveness of the heat exchange process. Okay, how do you increase the heat transfer coefficient? If I increase the heat transfer coefficient, does it improve the effectiveness of the heat exchanger? So as I just now told that if I increase the heat transfer coefficient, it should increase the effectiveness of the heat transfer process. So then if I increase the air speed, I should get more effectiveness. People who have done the experiment should be able to tell this. If I increase the air speed, do I get more effectiveness, or do I reduce the effectiveness? Just think on this aspect. I think two groups have already finished this air conditioning experiment. We have done one experiment on the air conditioning simulator where we have increased the fan speed. We've increased the fan speed, and the common understanding is I should be able to increase the effectiveness of heat exchange process if I increase the fan speed. But what was actually observed in the experiment? Do you remember? Let's say this is your ADP. Okay, I have a certain air speed, and I get this as the exit air condition. If I increase the air speed, will this point move here, or will this point move here? Given that the coil temperature is same, given that the incoming air temperature is same, if I increase the air speed, what happens? Will the exiting air move here, or will the exiting air move here? Increasing the airspeed. This we have done in the experiment. Given that all the other conditions on the refrigerant side is same refrigeration capacity, everything is constant, what happens? This should be very easy to answer.
So it will move to the right.
It move to the right. Exactly. So our common understanding says that increasing heat transfer coefficient should improve the effectiveness. But if I increase the air speed, what happens is the temperature now moves towards the right instead of moving towards the left. And it has to, because it has to satisfy the first law. Okay. So in order to improve the effectiveness of your heat transfer process, you actually have to reduce the air speeds. And again, this is what your air conditioning system does when you move to your dry mode. It will move to a lower temperature, and it will also move to a lower velocity. You will not be able to control the fan speed with your remote then. If you move to your dry mode, you will see that the option of setting the fan speed is taken away from you. Because if you set it at a higher velocity, you will end up over here. But you eventually want the air coming out of the heat exchanger as dry as possible. So the manufacturer will move to a lower fan speed actually. So many a times while using heat transfer coefficient, we forget about MCP delta T. So if I reduce the m dot, I increase the delta T of air across the coil. So please understand that effectiveness is just defined on the basis of the temperature differences. So maximum potential on the denominator and actual whatever happens. Okay, so then in that case, if you move to a smaller and smaller speeds, you will have much larger temperature drop across the heat exchange. Actual experimental data I have given over here. If you have more number of rows, so this is bypass factor. So if you have to get back the effectiveness, you have to do 1 minus bypass factor. So if you have more number of rows, you see bypass factor reduces. So it's almost 96%, 97% effectiveness. Okay, if you have smaller air speeds, you see that again bypass factor is less at smaller air speeds. Okay, but I do not have the data for variable fin pitch because this fin pitch was constant for the heat exchanger. So basically, if you want to understand what is improving the effectiveness is residence time for heat transfer and mass transfer. So what will increase the residence time? If you reduce the air speed, it will take more time for the air to travel across the coil and it will have more time for the condensation process, for the heat transfer process. It will cool more. You get the same inference if you apply your first law across the coil. If you have to have a steeper slope across your cooling coil, given that your refrigeration capacity is constant, you have to provide a much smaller air speed. Now, when you actually do the analysis of your experimental data, there is a possibility that you might end up with a process like this. So if you are using cooling and dehumidification coil, this is your limiting case. Okay, if I ask you to provide me more dehumidification, you will see that you will not be able to have this line touching the RH equals to 100%. In case you desire an exit condition here, that is possible because if you extend this line, it touches the RH equals to 100%. If you want an exit condition like this is possible. All these lines are possible. But if you desire a line which is this, then this line is not possible. This process line is not possible using your cooling and dehumidification coil. So then what you need to do is you need a multiple sequence of processes. You may go here. Okay, then you may have to heat it up. Okay, maybe up to here, and then again you may have to cool it like this. So you may have to go through series of process, or if at all this is also not possible, this, then again cool, and then again. So now this helps you to understand that why in your central ACs we have cooling coil and reheating coil. So cool, reheat, cool, reheat. Okay, in the experimental setup also we had one cooling coil and one reheating coil. When your desired process lines do not yield any apparatus dew point, if you extend this line, it will never touch the RH equals to 100 line. Then you have to resort to such multiple staging of the process lines. Cool, reheat, cool, reheat. I'll stop here. So people who have already done the experiments, please do the analysis part of the air conditioning experiment now. I think whatever